everyone, welcome back. This is another lesson in ray optics by Alpha Beta Gamma. And in this lesson, I am going to explain a very important topic which is Snell's Law. This is also called Snell's Rule. And what is this Snell's Law about? This Snell's Law is about the refractive index of the given material mu. In the previous lesson, I explained the refractive index of the given material is the ratio of the two velocities in the given two materials, V2 divided by V1. This is the relative refractive index between the two materials. And if you consider the light propagating from air or vacuum to any other material, refractive index of that material, mu C by V. This is absolute refractive index and this is relative refractive index. And what is this Snell's law? This is also a formula which expresses the refractive index in terms of the angles, angle of incidence and angle of refraction. In 1611, a Dutch scientist, Snell, he discovered and derived. He was an astronomer and mathematician. He derived a formula by explaining the propagation of light in terms of velocities in the given two materials. Now I am going to explain Snell's law, Snell's formula for refractive index of the material. For that, here we have a diagram about the refraction of light. This refraction of light, here I have taken the case, consider the case, the light propagating from rarer medium to denser medium. This is medium 1 and we can consider it as a air, rarer medium, and denser medium 2, maybe water. And this refraction is from rarer medium to denser medium. As I said, due to refraction in this phenomena, there is a change in the velocity of the light after entering into the second medium. It means the velocity of light in the rarer medium, that we can denote as V1, and the velocity of light in the denser medium, we can denote it as V2. These two velocities are not equal to each other. The reason is, when the light is propagating from rarer medium to denser medium, due to the change in the density, its wavelength is changed and its path is changed, its direction is changed. So due to this change in direction and the path and wavelength the light, the velocity of the light is changed. So now we are calculating refractive index in terms of the angles by considering the direction of the velocity. These two velocities V1 and V2. If you observe V1, this is the direction of the V1, which makes an angle I with the normal or perpendicular line drawn to the surface. And direction of V2, it makes an angle R with a perpendicular line. And so I and R are the directions of the two lights. We can resolve the velocities into two components. One parallel to the surface and two perpendicular to the surface. So the two velocities can be resolved into two components. Here I'm going to explain how the two velocities are resolved. So this is about the velocity of light in the first medium. This is about V1. Now V1 is resolved into two components. This is the boundary which separates the two media, 1 and 2, rarer medium and denser medium. Velocity of the light, this is V1, which makes an angle I with the perpendicular line here. So it can be resolved into two components, one parallel and two perpendicular to the surface. Parallel to the surface is V1 sin I and perpendicular to the surface is V1 cos I. So parallel component will be V1 sin I and perpendicular component will be V1 cos I. This is resolved into two components. In the same way, we can resolve the velocity of the light in the denser medium. Now we will talk about the velocity in the denser medium, which is about V2. So the boundary which separates the two media 1 and 2, normal drawn to the surface, and this is direction of the velocity V2 in the denser medium makes an angle R. It also resolved into two components, one parallel to the surface and two perpendicular to the surface. Parallel to the surface, this is V2 sin R. Perpendicular to the surface, V2 cos R. So the two velocities V1 and V2 are resolved into parallel and perpendicular components. Now, we will speak about the perpendicular components first. Here, the parallel components are equal. Why the perpendicular components are not equal? Why V1 cos I is not equal to V2 cos R? Here, V1 sin I equals to V2 sin R. The parallel components are equal, but the perpendicular components are not equal. What is the reason? So, Snell, he discovered that when a light particle is traveling in a medium, in any material, it experiences a force. A force is applied on the light particle which moves the particle in the perpendicular direction of the surface. So a perpendicular force is acting on that. But this force depends upon the density of the material. Therefore, the perpendicular component V1 cos I and V2 cos R not equal to each other. But there is no any force acting on the light particle parallel to the surface. This is the reason why the parallel components are equal. So, equating the parallel components, V1 sin I equals to V2 sin R. So, parallel components are equal to each other. Now, I will take the ratio V2 by V1. If you take this ratio, and this will be sin I divided by sin R. So this is the ratio of two velocities. Where did we get? This is from this equation. V2 divided by V1 equals to sin I divided by sin R. I said the ratio of the velocities V2 by V1 is equals to refractive index, relative refractive index of the two material. So this relative refractive index, which is equals to V2 divided by V1, we can express in terms of sin I and sin R. It means mu equals to sin I divided by sin R. So this is refractive index of the relative refractive index between the two materials. So this mu value in terms of the angles, sin values of the angles derived by Snell. This is the Snell's rule, Snell's law, where it is used and how it can be used. We can calculate a refractive index of the material if you know the direction of the incident light and refracted light. If I and R values are given, we can calculate refractive index. Or if you know the refractive index value and direction of any one of the two lights is known, then the direction of the second light can be calculated. And this is also used to calculate a refractive index of the materials like a glass, lens and prism also. Prism formula for that is the refractive index for the prism formula for different colors can be calculated using Snell's rule only, but it is in terms of the angle of deviation that I will explain in the next coming lessons. So this is about Snell rule. Sin I by sin R equals to refractive index of the material. This is very, very important. That's all for this class. And in the next class, I'm going to explain one more important point, optical path. Thank you for watching this video.